The goal of our project was to create an algorithm which could maximize the profit through the trading of cryptocurrencies. We used 1-minute interval data from Bitcoin, Ethereum, and Zcash. We averaged the opening and closing market rates for each minute to extract a market rate. In order to measure the efficiency of our algorithm, we create two control base cases. For the first control, the agent sells or buys all the coins that he can when the market rate changes. For the second control, the agent acts more cautiously. He sells or buys 10% of all of the coins that he can when the market rate changes.
In order to answer the question of how to maximize profit through the selling of cryptocurrencies in a short 20-minute window, we decided to model the problem as an MDP that we could solve through value iteration. In order to do this, we had to limit the number of actions as much as possible, because otherwise the state space would grow exponentially out of control. To accomplish this, we limit our actions to just two: trading, where either all of our cash is spent on buying coins or where all of our coins are liquidated into cash, with the other action being holding, where our assets remain unchanged. Following our action space, the state of our environment is made up of three components: 1, our cash on hand; 2, our inventory; and 3, the current market price for the coin. To keep track of all of the different spaces, we decided to implement a tree with the rule: anytime a hold action occurred, the next state would become the left child of the current state. Anytime a trade action occurred, the right state would become the right child of this current state. With our environment established, we move on to the simple task of Q-value iteration. Our reward function is simply the sum of the cash on hand plus the revenue we'd earn from selling all of our coins at the current market rate. A transaction function uses a heuristic that states that there is a 90% chance that any trade action complete, and a 100% chance that any hold action will complete. Once the v-values have been calculated, the algorithm outputs the maximum profit possible in these states in our time horizon of 20 minutes and outputs the trading decisions required to get there.
We tested our agent over 100 randomly selected 24-minute intervals of our average market rates. The base case control algorithms returned a loss. We observed that the algorithm where an agent acts impulsively at high risk, trading all of his inventory, suffered a smaller loss than the algorithm where an agent acts cautiously. Our algorithm returned a profit of 0, which can still be considered an improvement, as our algorithm did break even, whereas the base cases returned a loss. Going forward from this implementation, we could consider implementing an approximate Q-learning algorithm with weights on a feature-based representation. Another algorithm which could be applied to this scenario is the deep Q network algorithm. In a deep Q network, a neural network is used to approximate the reward based on the state, similarly to the Q function, which calculates the expected future value.